All right, so that explains how that first condition is satisfied, that it's basically taking care of the averaging over noisy transitions. This second condition is going to turn out to be, well, let's find out what it's going to turn out to be. So what we're doing here is we're saying, let's apply this operator, this BTQ operator, or BTQW operator. And the condition that we need to have hold is that for any Q, U, S, and A, that if we hold this U fixed, right, which is in the Q learning equation, is going to turn out to be the Q itself, and only vary how we're computing our one-step look ahead, right, how we're estimating the Q values of states that we are moving to one step from now, that the difference between those two Q functions, in this case Q star and Q, is going to get smaller after we apply this operator than before, which is an example of what property? Like, what is it about the operator that we're counting on for this to be true? That before we do the one-step look ahead, they're some distance apart, but after they're closer.
Actually, I'm not sure.
So, however far apart the value that we're using as a one-step look ahead, however far apart it was before, that after we apply this rule, it's closer together.
Right, and they will be because you're moving in the direction of what the one-step look ahead operator said.
Right, and so what property the one-step operator, what property of this equation is giving us that? It's the contraction property. All right, so the fact that this update has the form of a contraction is what gives us this property being true. That after we apply an operator, things get closer together.
Mm-hmm.
So, and then the third condition was just the condition on the learning rates, and we need that for any kind of Q-learning algorithm anyway. So at the end of the day, by separating the Q-learning update equation into kind of using two different Q functions in two different ways, we can prove properties of both of them. One is playing the role of averaging out the stochasticity, so that we're sort of acting as if there are expected values in here, even though there's not. And then given that, the other one is acting like the value iteration operator, the one-step backup, and is contracting with respect to the value function that you used. So there's again the Q values the Q functions are being used in two slightly different ways. We prove that both of them hold, and therefore this theorem gives us that the whole iterative algorithm is going to converge.
Right.
So this is all really just a long way of saying, hey, look, because Q-learning can be forced to fit into this scheme, it's guaranteed to converge in the limit.
All right. So Q-learning converges.
Q-learning converges.
I mean, I guess we knew that.
Yeah, we knew that. And in fact, there's a long literature where people have proven essentially this result over and over again in slightly different ways using different tools. The thing that I like about this proof is, well, first of all, I read it because it's in a paper that I wrote. But second of all, it breaks things down in this sort of modular way that we're going to be able to reuse to prove the convergence of other Q-learning-like algorithms. And that turned out to be important to prove, for example, that Q-learning in game scenarios also converges.
Huh. But that's in the future.
That's in the future.
Are you going to reprove this all over again when we get to the future?
No, we don't have to, because the generalized theorem holds in both cases.
Nice.
That's the beauty of the generalized theorem. We never have to look at this again.
Well played, sir.
All that's going to matter is, well, it's going to matter that that the operators that we use for updates are contraction mappings.
Okay.
And as long as we take care of that, things are going to be great. Oh, sorry, non-expansions. As long as the kind of the thing in this position here is a non-expansion, all will be well.
Good. So well played. So we went through all this so we never have to go through it again. I like that.
That is exactly the thought. Yeah. And in fact, even missing all the details of this, I just wanted you to be aware of the fact that these details exist. The way that we actually use this is at a much higher level of abstraction, where we just say, hey, we can write down what we think the Bellman equation is. We can prove that the operators that we're using here are non-expansions, and we're done.
And we inherit everything else. Yeah, it's just like knowing that the sum of the alphas should go to infinity, but the alpha squared should not go to infinity. Once we know that, then it helps us to decide whether to choose this learning rate or that learning rate. It's the same thing. We can't just substitute max with any arbitrary thing we want to, because it might be expansive instead of non-expansive. But so long as we're smart about the things that we pick, we know that things are going to converge.
Exactly. And so let's maybe go through some examples of that as a quiz.
Sure.